All right. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet and study your creation. Help us to, again, Lord, to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. Okay, so let's get straight into it. To start with, now I think Dr. Schmidt talked about this earlier, but the definition of, if you have a, it's a little much. If you have, there we go. If you have a mapping, I say a linear transformation, although I think, linear transformation from normed linear spaces, or also known as like a normed vector space, right? From V to W, we define the norm of the transformation by the supremum of the norms of the image of the transformation under the basically unit ball. So look at the inputs which have unit length and see where that maps to, and the supremum of those, that defines the norm. And if the supremum doesn't exist, then you can say that the norm is infinity, and then you'd say T is an unbounded linear operator. Now, I don't really pursue this much. I don't think any of the operators we're going to look at are like this, but this is if you were to continue this discussion in graduate school, you could look at, operators which had bounded norm and the operators which did not. And so this is a whole direction for discussion in graduate analysis, functional analysis. But one of the easy calculations we could do here is like this. If we have a linear transformation from V to W, where V and W are normed linear spaces, then if the norm is less than infinity, if it's bounded, then the norm of T of X is less than or equal to the norm of T times the norm of X. And so here's how that goes. So if X equals to 0, obviously true, right? Because T of 0 is 0, and norm of 0 is 0, 0 equals 0, yay. And on the other hand, we can rewrite any vector that's non-zero as 1 times itself, right? But then if you pull that out by linearity of T, then you've got this. But what's the norm of X over norm X? Well, it's 1, right? That's a unit vector. So as such, this has to be, and then of course we can also pull this out because it's a real constant, right? Properties of the norm. And this, of course, is going to be less than or equal to the supremum of the values which T takes on the unit ball. So we have less than or equal to X times norm T. So there you go. That's one of the reasons that the norm of a linear operator is interesting, is because it gives you this bound on the norm of its outputs. So now let's see here. So at this point, when I was typing these notes, I was still kind of thinking, I'm going to figure out how to rewrite Edwards, and because Edwards makes some, in my opinion, kind of bizarre choices in his choice of norms and things. But I after a while, I was like, I mustn't let perfect be the enemy of good. So I just humbled myself to follow Edwards, and that's what we're going to do. So. All right, so first of all, definition, he's going to use, and X sub naught, he calls this the max norm. Now, I technically think that this is often denoted X infinity, because I think if you just think about this formula, what happens as P goes to infinity, it makes the larger values way, way larger. And it makes smaller values considerably less large compared to the largest value. If you think about P going to infinity, I think it makes sense that basically this is going to be totally dominated by whichever component's largest. So in the limiting sense, I'm pretty sure this gives you the max norm. But nevertheless, I'm going to follow Edwards and call it sub-zero. So that's my first complaint. But anyway, so the max norm of a point in Rn You take the maximum of the absolute values of the components. And again, this is something Dr. Schmidt talked about in one of his lectures, right? A little bit. So in this case, the n cube of radius r greater than 0 is defined to be this. You know, technically speaking, it's the n ball of radius r greater than 0 with respect to this norm. But we're going to call it a cube because it is a cube. Because it's actually given by, you know, the max norm being less than or equal to 1. And if you look at that, well, here's what it looks like specifically. In 2 dimensions, the r cube is like going to be the direct product of Cartesian product rather, of minus r to r and minus r to r. So it's just a, you know, it's a square centered at the origin with side length 2r, right? C3r would be the cube of side length 2r centered at the origin, and so forth. All right, so like the n-dimensional cube would be the Cartesian product of minus r to r n-fold times. And the boundary of these n cubes is relatively easy to understand, which is part of what makes all this like work together nicely. Come on. Like for instance, the boundary of the 2 square is this, which, let me just do a little bit of drawing today. I'll add a small amount of value with my notes here. Let's see here. Orange, blue, red, black. That should do it. So this would be like this one, right? And then that would be this one. And then that is this one. And then the final one is this guy. So this would be minus r to r, Cartesian product with r. Down here, minus r to r, Cartesian product with minus r. You should write it sideways. All right. So don't say I didn't write anything today. Okay, but anyway, that's the boundary. And of course, the 2 cube itself is everything inside, right? I mean, okay, so all right. So moving on here.
Am I misunderstanding something?
I don't know.
Or
I can't read your thoughts yet.
should C and R be defined where the maximum is less than or equal to R?
Yes. Yeah, that's a typo. Thank you. You are correct. That is supposed to be R. Yep. Yes, thank you. So if you look at this, if we have x in the boundary of, you know, the n cube, there's at least one coordinate xj for which the absolute value is equal to r. Did you guys see that? So like on the boundary, there's at least one coordinate which has absolute value equal to r. That's the nature of the boundary. All right. So proposition here, if x is in the boundary of the n cube, then the max norm of x is equal to r. Okay, that's just kind of obvious from what I just said. Okay, because it has a component which has magnitude r. Yeah, proof by what we just did. Definition. if we have a linear transformation from Rn to Rm, then and so here I am defining the norm of L with the max norm of L, all right, to be the maximum of the maximum of the one norms of L of x, where x is taken from, the boundary of the 1 cube. Okay, so this is a specialization of the norm I started class with. I'm looking at the specific, implementation of that concept with respect to the max norm. Now, notice that this definition makes sense because if you look at it, x maps to this. It's the composition of continuous maps. I think that's a thread about a homework problem, which I made good on in the homework I just posted today. And it follows from the extreme value theorem that the maximum value exactly attained, because that's a compact set. And as such, the extreme value theorem says if you have a continuous function with a compact domain, it attains a maximum and a minimum, and in this case, the maximum. So the norm of L is defined for any linear transformation from Rn to Rm. And following the proposition that we just stated a second ago here, we can see that the norm, same argument, just with now max norms instead of arbitrary norms, that the length of L of x is less than or equal to the length of L times the length of x. All right. And in fact, we can say more. If m is any constant that bounds L in this sense, such that the length of x is less than or equal to m times the length of x, then the norm has to be less than or equal to that bound. In other words, let me put it into words. It's saying that the bound provided by the norm of the operator is the best bound you can get. It's the smallest one. All right. Any other bound that you can find, it'll beat it. It's the best bound. And so here's the proof. If x is in the boundary of the n1 cube, then of course the norm of x now is equal to 1. Thus, L of x now is less than or equal to m. However, by the definition of the norm of L, we also have that the norm of L is less than or equal to the norm of L of x, which then shows you that this is less than that is less than that. Hence, and this is missing the 0. I just missed it. I got to fix that. I'm sorry, guys. So if you do look at Edwards' Advanced Calculus, and I still don't have a favorite analysis book, but this is the book that I've learned a lot from, so I've grown fond of it. But other people are critical of it. I don't know, whatever. But it's a Dover book, so it's it's cheap. But I've learned a ton from this book, and but in Edwards, he doesn't put the subknot on the operator norm. His just looks like this. So if you do look at the book, my notation is not totally in sync with it. I've made some adjustments, but anyway. So next up here, it's C.H. Edwards Jr. to give the full title. I don't know what the H is for, now that you mention it. He was at the University of Georgia. And it's got I don't think it has any personal information before, like, the math. Not really. Just a little bit about, like, a class he taught that led to the book, I think. Anyway. I really don't know much about the man besides that. Anyway, so here's a theorem. If we have a linear transformation from Rn to Rm, and it has component functions, L1 through Lm, then the norm of the component function will be less than or equal to the norm of the whole mapping. So the proof is pretty easy. So if you have one j being between 1 and m, you pick a point on the boundary of the 1 cube for which the norm of the jth component function is realized. We know such points exist. Regret using x naught for the point here. I was going to come back and edit it and change it to a z, so I would have less knots in this.
Now you're all tied up.
I'm still all tied up, yeah. So how where I was going with it. All right, so anyway, so here we go. So that's the point at which the maximum is attained. That has to exist for the reasons we just talked about. So then the norm of the jth component function is equal to that, but that's less than or equal to the maximum of the values at that point for all the component functions, right? I mean, this is just duh, and proof by duh. But that is by definition the norm of L of x naught, which is less than or equal to the maximum of all possible things in the unit 1 cube, right? So I don't know that the x naught, which maximizes the jth component function, is the same x naught that maximizes the function as a whole, like the linear transformation as a whole. But I'm still allowed to like connect the two thoughts because of this string of inequalities here. But that is the norm of L naught. So there you go. So yeah, that was pretty. The arguments are pretty easy when you work through them. Now it would be crazy tiring for me to write everything out I'm telling you today in a lecture. Like I would be totally. I'd go fall asleep afterwards. Like it'd be so tiring. So I'm going to keep using the projector because I have a lot to say. Anyway, so here L is Rn to Rm has a standard matrix A. We know what that means, right? The formula for the standard matrix, I would remind you, we can write like this, right? It's L of x is equal to row 1 of A dot x, row 2 of A dot x, dot, 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 row m of A dot x, right? That's a way we can look at the formula for A times x. So if we take x in the boundary of the 1 cube, then if we think about it, the ith row of A dot x will be largest if we make x equal to ek, where aik is the largest magnitude entry in the row I of A. If you think about like how would you maximize, get the biggest bang for your buck by, plugging x in? Like how would you get the largest choice in a particular component? Well, you'd make x match up with the component which is largest in the row, That's all I'm saying.
Assuming x is normalized, the vector?
Well, x is an element of the, here x is an element of the 1 cube, but thankfully the standard basis is counted among these. Because the standard basis is 1, 0, 0, 0, or 0, 1, 0, 0. So standard basis is in the 1 cube. They're, I suppose, vertices in the 1 cube. But anyway, well, are they vertices?
Middle of the side.
They're not vertices. They're in the middle of the side. Yeah, thank you. Let's not say let me try not to say dumb stuff today. It's too late. It's too late. That's already gone. So anyway, this is just a motivational. I just wanted to give kind of like a little motivational talk about why the definition given below is given, rather than just have it completely unmotivated. So I've almost motivated it. So for reasons related to the paragraph above, we're going to define the norm of a matrix for the purpose of this lecture, and your homework, I suppose. But anyway, so the norm of A is going to be the max of the 1 norms of the rows. The 1 norm of the row is defined to be the sum of the absolute values of the components. So like for me, personally, from like a mathematical perspective, this is kind of, there's something wrong about it, because it's like mixing the max norm with the 1 norm. It's like, but it works. It works beautifully. So let's just, I accept it. I'm going to use it. But it is weird in my sort of natural reaction to this definition. It feels weird. But anyway, so the max of the 1 norms of the rows is the norm of the matrix, the max norm of the matrix. All right, so in other words, you could write this formula. The norm of the max norm of the matrix is the maximum 1 less than or equal to I less than or equal to m of these guys. This is just the sum of the absolute values in the jth row. Excuse me, in the ith row. But look at what it does. The payoff's down here. If we have a linear transformation with standard matrix A, then the norm of L, the max norm of L, is the max norm of A. So this makes the mapping that goes from the set of linear transformations to the set of matrices. It makes the mapping like L maps to standard matrix of L. It makes it an isometry. It makes it a distance preserving map because the length of the linear transformation is equal to the length of the matrix to which it corresponds. So that's pretty nice. In my experience, a lot of times those kind of isomorphisms tend to come with some kind of multiplier or something with respect to the distance. It's like, or they're just not directly related to distance, but length of the vector, I mean. Anyway, here's the proof of that. So if you calculate, the max norm of L of x, well, that's this, but that's less than or equal to this by, basic inequality stuff, which is less than or equal to the max norm of x, right? Because notice that this is larger than anything possible here, right? Remember, this is the maximum component in absolute value for x. So if you were to write this, I mean, we can of course write this as the product of aij's norm, absolute value, words. This can be rewritten as the absolute value of aij times the absolute value of xj. But the absolute value of xj is essentially by definition less than or equal to the max norm of x. But then you got this, but that's exactly the norm of a, the max norm of a. So we have this is less than or equal to that. Thus the supremum of L of x naught is less than or equal to that, right? We're trying to show they're equal, so what do we need to do?
Show that norm A is less than or equal to norm A.
Right. So let's think back. We also know that the previous proposition that the ith component function of the linear transformation is less than or equal to the length of the linear transformation as a whole. And so that tells us that Li, since this is bigger than that, we also have that, the max norm of A bounds the norm of each component function. But then we can basically do the same trick we already did, which is to pick the point which maximizes the ith component function, z. So Li, see, I had the good sense of calling it z here. I was going to go back and change the other x naught to a z, but I didn't do it. Sorry. Anyway, so you use z. I'll allow it. So, wait a minute, is that a Lizzo?
Lizzo. Dr. Cook. See, I look at math writing and think of words that are not great. And now you're just confirming that other people do it too.
I don't know what you're talking about. Lizzo's beautiful. Let's see here. So,
I'm just talking about the association of math text to other things.
Sorry, I should stop. So I think, yeah. So, so it follows then. Oh, okay. So this is. Good grief. Where was I? Oh, if we can find z for which this is equal to that, then it follows that Li is equal to that, and then by extension, L has to be equal to that, right? The norm of L has to be equal to it. Okay, so we just pick the special choice of k for which rho k, the one norm of rho k is greater than or equal to the one norm. I missed my one norm over here. There's a 1 missing there for all I going from 1 to m. So observe that the max norm of the matrix is equal to the one norm of that maximizing row, which I'm calling k. All right. Oh man, that's right. This construction is goofy. So then I'm going to introduce sine of r to be 1 if r is greater than or equal to 0, minus 1 if r is less than 0. And I'm going to let zj equal to the sine of akj, that max row. And so what that does is it gets you the biggest bang for your buck out of the max row. See, because when I take, the kth row of L of z, the kth row of az then, in other words, row k of a dot z, that gives me the sine of akj, which is, so if it's minus, if this is negative, this is minus, which makes this absolute value. If it's positive, this is positive, which makes it absolute. In all cases, you get the absolute value of ajk by multiplying by this rather sneakily constructed z. And as such, that gives us the one norm of row k of a, which, by construction is the max norm of a naught. So this proves that the norm of the kth component function of L is actually equal to the max norm of a naught. But we also know that that's less than or equal to the norm of L naught. Thus, a naught is less than or equal to the norm of L naught. Consequently, they're equal. Yeah. That's an argument. So this is basically in Edwards. He uses a slightly different notation, but that's the idea. All right, great. Proposition: if L from Rn to Rm has L of x equals ax for all x in R, then L is continuous. All right. Suppose x. Wait a minute. Did I make that a homework problem? I think I made that a homework problem. Don't look at this.
Yes, you did.
No, I didn't. I didn't. Haha. I didn't. I made it a comment in the homework problem. Ha.
When's the homework due?
Ha. Thursday. All right, I better get to it. I need to help you guys with the last homework problem today.
Oh, yeah.
Like the last homework problem is complete the last proof.
It's complete what?
Complete the last proof.
In here?
Yeah. So, let's get to it.
Rest of it is routine.
Yeah, that's right. Okay, so moving on here. To prove that, well, anyway, this is a routine calculation. I don't think this actually matters to us. I'm going to skip past this part. Well, I'll regret if I need this later. Let me just take a second to talk through it. So to prove something's continuous, how do I do it here?
X element, Rn.
So if x an element of R, x not equal to 0, we can then write it as its unit vector times its norm. L of x naught, the max norm of L of x is this, which is less than or equal to that. Okay, great. So for x not equal to a, I can write this is equal to that by linearity of L, but that's less than or equal to the norm of the max norm of x minus a times the max norm of a naught. So I'm just using the toys that we've just developed in the last page, right? Great. So let a be an element of Rn, assume that the max norm of a is not equal to it's just not equal to. I believe there's a missing 0 there. So, yes. Or you could say that the 0 is white. Or possibly this is a 0, it's just in a very small font.
Small font 0.
Small font 0, okay. Anyway, this is supposed to be non-zero. If the norm of a is equal to 0, then that means that the mapping is the 0 mapping, which is easier. I leave the proof that the 0 mapping is continuous to you guys. That one's easier. So let's suppose it's not the 0 mapping. Let epsilon be greater than 0, choose delta equal to epsilon over the max norm of a. If we're within delta units of a in the max norm notion of distance, then the norm of this guy is less than or equal to that times that, which is less than or equal to epsilon over max norm of a. They'd be canceling, you get epsilon. Continuity, yay! A was arbitrary. Therefore, it's continuous on the whole shebang. All right. Like I said, that's not my usual. I enjoy proving continuity of the linear transformation with respect to the Euclidean norm in advanced calculus typically. Because like I don't know, I'm still on the fence as to whether or not I'm going to implement some of these things into the advanced calculus course or not. I don't know, I need to think. I need to look at the audience. If there's engineers, it's a game changer.
I think we have 2 engineers so far.
Uh-oh. All right, so.
You should just do whatever you want to do.
Yeah, I should. I should just do whatever I want to do.
I know them both. They're smart enough. They'll be fine.
Okay, that sounds good. Like I said, there is a proof of continuity in my advanced calculus course, which does not require the special max norms definitions given in this article. Basically there, I just let m be the maximum of all the absolute values of the components. And you can use that to get a simple bound on the output of the linear transformation based on the size of the input. But anyway, moving on. If f is a mapping from, I added the ends. When I posted the note, did I post the notes? Did I post the PDF of the notes in Canvas? I don't know if I think I may have forgot to do that. If I have, I'll try to do it later. In any event, I added the ends. I was missing them some places. So let f be a function from Rn to Rm, differentiable on U. We say f is continuously differentiable on U if each partial derivative function is continuous on U. In this case, we say f is an element of C1U. All right. So let's think about this. So since JF, the Jacobian of f, right, has component functions which are partial derivatives of the components of f, it's also true to say if f is an element of C1U, well, it's true if and only if the mapping P maps to the Jacobian of f at P is continuous. Right, so these are two different concepts, right? The one is continuity of each partial derivative of every component function versus the continuity of the mapping P maps to a matrix assigned to P. Those are different maps, but the continuity of one and the continuity of the other, they're equivalent because we have a theorem that if you have a mapping, it's continuous if and only if all of its component functions are continuous. And the component functions of a matrix you can think of, well, literally as the component functions. Anyway, so on the other hand, the differential is the assignment of a linear transformation, dpf, for each p and u, right? So to say that the differential is continuous on u means for each epsilon greater than or equal to 0, we need to be able to supply a delta greater than 0 for which if we're within delta units of p, and I'm going to use the max norm sense, not equal to p, right? That's why the 0 is here. Well, that has to imply that, wait a minute, continuous. I don't need this. Yeah, this is a mistake. This is a mistake because continuous, we examine the point, not just points near the point, right? Yeah. Sorry about that. We gotta fix that. My bad. As I've warned you guys, I don't have an editor. You're the editors. So that implies that the norm of dxf minus dpf is equal to 0. Now, so notice that the max norm of dpf is equal to the max norm of the Jacobian matrix because the standard matrix of the differential is the Jacobian matrix. And we just proved that the max norm of the linear transformation is equal to the max norm of the matrix of the transformation. Therefore, that's why we have this equality. All right. But since the Jacobian matrix, oh, I just said that. Consequently, the max norm of dx minus dp of f, right, is equal to the max norm of jf of x minus jf of p. Therefore, if f is differentiable on u, then we can think of the mapping as being continuously differentiable in 3 equivalent manners. There are 3 ways we could consider the continuous differentiability of a map. 1, the differential is continuous on u. This is by far the most esoteric viewpoint, but it's the most natural viewpoint. To say continuously differentiable would mean you have a continuous assignment of the differential. The differential is the derivative of a map. That's the natural idea of the derivative. The Jacobian matrix is kind of a more coordinate-based formulation of it, you know? But that's the one we could talk. We could mean continuous differentiability means that df is continuous, which is actually, you know, the pointwise assignment of a linear transformation. Or we could say that the Jacobian matrix is continuously assigned on U, all right? Or we could say that each of the partial derivatives is continuous on U for every possible component function and derivative, right? These are three logically different ideas, but they're all equivalent with this setup. And typically in undergraduate math classes, we define continuous differentiability in terms of the continuity of the partial derivatives, because everybody knows about these, whereas 1 and 2, not as many students really understand what I'm talking about there, and that's why textbooks shy away from that way of thinking. But anyway, all right. That doesn't really help us prove anything here. It's just as a point of mathematical sightseeing while we're at it, okay? So, you know, I don't think we're going to be in the midst of like the deep theorems that follow and be like, oh, and by this trichotomy of viewpoints. That's not what I'm talking. This is just, you know, mathematical sightseeing what we're doing at the moment. So some of these things I'm not going to prove in here, but I will prove in 332, but I'm stating them here because they're part of the discussion. So this, if f is continuously differentiable in the sense that all of the partial derivative functions are continuous on U, then f is differentiable on U. So you almost saw a decent proof of this in the two-dimensional case in complex this semester already. But I will do the genuine proof in n dimensions in advanced calc next semester. All right. So it takes me about a half hour to do this decently. Okay. So that's a deep theorem. And so that brings us to our main goal for this section, which is the generalization of the mean value theorem for maps. And here it is, the mean value estimation theorem for maps. If you have a mapping from Rn to Rm, continuously differentiable on the open set U, and you've got a line segment from A to B in U, then the max norm of the values of the function, the mapping rather, over the line segment is less than or equal to the max norm length of the line segment times the maximum of the values that the the Jacobian matrix takes as you sample points along the line segment with respect to the max norm. Of course, we could just as well put dfx here, right? Like I've just put the Jacobian matrix because I think that's the most friendly thing to put here, but you could just as well put dfx. That would be the same. So let's look at the proof. So first of all, we parameterize the path from A to B in the usual way. All right. Well, that's not quite true. This is not the parameterization of the path. The parameterization of the path is in here. That's the usual parameterization from A to B, right? Gamma of t is the image of that linear that line segment under the mapping f. So this would be some kind of curve in Rm is what that would be. Right, and so by the chain rule, which I will not prove here, but I will probably prove in advanced calculus, at least in some, maybe proof is too strong a word. I will describe the chain rule. Oh yeah. So the gamma dt is equal to df at a t plus hh, but what I'm really saying, so the kth component of it is the differential of the kth component of f evaluated. So this is just chain rule, like the inside function is a plus th. I've defined h to be b minus a. It's not too much really going on here. So a plus th is this. So we've got f of a plus th. So we have like the derivative of f at the inside function, a plus th, times the derivative of the inside function. But the derivative of the inside function here is b minus a, which is just h. That's all. It's really just the chain rule here. So anyway, here you go. Max norm of f of b minus a naught is equal to the max norm of a particular component. This trick always is somewhere in these proofs. So since the max norm is the maximum of a particular component, it allows you to trade the max norm of the whole thing for the max norm of a particular component function, which is what we do here. Oh man. I think I'm missing a 0 there. So I just don't know anymore. Maybe that's actually just, no, I think this is fine. This is it's fine. I'm not missing a 0. Remember, this is the max norm of the components. So this is a vector in Rm. We're taking the max norm of it, which is the maximum of the absolute values of the components. So if the kth component is maximal, then with the kth component function, there's no 0 missing. I'm wrong. Now this is just the definition of gamma k. And this is a dirty trick. So the integral of the derivative, see, so you can convert a difference to an integral of a derivative. If you study proofs of Green's theorem, Stokes' theorem, divergence theorem, all the major theorems, they all use this trick. This is the trick often used. So right there, but then by properties of the integral, that's less than or equal to the integral from 0 to 1 of that, the continuous. It is, you're right, that is the triangle inequality passed through the limit of the Riemann integral. Sorry, all my integrals are Riemann integrals because I don't understand measure theory well enough to claim otherwise. But anyway, so then that is by the chain rule we wrote before the thing, this, which is less than or equal to the maximum of this. If you think about the steps here, this is less than or equal to the integral from 0 to 1 of the maximum, but once you pick the maximum, it's independent of t. So the integral from 0 to 1 dt is just 1, which gives you this. The t here and the dt here are only coincidentally the same letter. All right. Those are fundamentally different processes we're talking about there. But anyway, there it is. And so, you thought we were almost done. You're wrong. So, we get to there. And then this is less than or equal to the max of what we got here. So here I'm using there may be a missing step here. I think this is less than or equal to the max norm of that. So like I could take this and I could slap a 0 here, I think. And then we had the theorem that that's less than or equal to the norm of the input, the max norm of the input, times the max norm of the operator that we were calculating, the max norm of the image of, I lack words. So we go from here to here. And then, let's see here. Then I've pulled this out. Clearly, the maximum of a constant times the norm is the same as the constant times the max of the norms. That's just a property of maximum. And then what we got here? Maximum 0 to 1. So this is the extreme value theorem gives such a tau. There has to be some tau between 0 and 1 that this norm is maximized at. All right? But then notice the k is gone. See, the k is gone? So now we're using that the norm of the whole differential is larger than the norm of the kth component of the differential. See that? And then this has to be, of course, less than or equal to the maximum norms of the differential taken over the whole unit interval. I mean, tau is somewhere in there. Yeah. Which then is less than or equal to the max from t goes 0 to 1 of that. But that is exactly all of the points that are in the line segment from A to B. Which means in terms of set theory, this is exactly what we wanted. Oh, goodness gracious. Like that. There you go. That's the mean value theorem in general. Corollary. Corollary. A couple corollaries. The corollaries are actually what we end up using in the inverse mapping theorem. So, let's see here. I can zoom in a bit. So corollary number 1.4.26, you got a continuously differentiable map. Then the difference between f of a plus h and f of a and L of h. So L is just some linear mapping, all right? It's not directly connected to f. It's just a linear transformation, okay? Then if you take the difference between difference of the change in f minus the linear transformation acting on h, well, that's less than or equal to the max norm of h times the maximum that the differential of x minus L attains on the line segment from a to a plus h. So the proof just follows from doing the theorem we just had with like g of x playing the, I think, let's see here. So g of x is this, dg is df minus dl. I'm not going to prove that in this course. We will prove that in advanced calculus. And a homework exercise is, now this homework exercise is real. You will show that the differential of a linear map is the linear map itself. That's an easy one. Thus, dg is df minus L. And if we set b equals to a plus h, we have h as b minus a. So g of b minus g of a is this. Something in here cancels out. Or I think I just rearrange it. So like here we have f of b minus f of, yeah, okay. Oh, I'm sorry, guys. My eyes are not working. So the first step is just straight up plugging b into this, right? F of b minus L of b minus f of a. Minus and minus gives me a plus, right? And then this term here and that term here, by linearity of L, give me L of b minus a. But that's h, so that's that term. And the other terms, it's not entirely obvious.
B is a plus b minus a.
Oh, okay, so that's that. Okay, so it's just that. Okay, great. We also know that the Jacobian of g is that which is equal to this. And then, so the corollary follows from the theorem then. Because this is g of b minus g of a, right? This is literally g of b minus g of a, and that's less than or equal to the norm of, max norm of b minus a, which in this case is h naught, and then the maximum of the differential of g taken over the line segment, which in this case the differential of g is exactly df minus L. Notice L has no point dependence because it's the same linear transformation everywhere, whereas the differential of x can vary from point to point. So it's a different linear transformation at each x. That's what makes the differential not quite something you've really thought about before this course or advanced. All right, and then corollary next corollary, 1.4.27, the motion of a cube by a map with an invertible differential. So if we have a continuously differentiable map on the open set U which contains the cube CR, now we're dropping the n because we're tired of it. F of 0 equals to 0 and df not equal to I, where I denotes the identity map on Rn. Well, okay, great. That's them's the preconditions. If in addition you have that the distance between the differential at x and the identity map in the max norm is less than epsilon for each x in the R cube, then the image of the R cube is a subset of the 1 plus epsilon R cube. Let me draw a picture of this as to not be accused of not drawing anything today. What's that? I know, but I mean, I should draw at least two things, right? So,
He drew 8 things.
yeah, so it's something like this. Here's the picture Edwards has, something like this. So here's, CR, and then out here maybe is your C 1 plus epsilon r. And then he draws the image under F. Oh man, look at that. That's supposed to be big F. See, Edward's got these little F's everywhere. I'm trying to change them all to big F's because I think it looks better. But that one slipped through the cracks. That's supposed to be big F. But, you know, F is not a linear map. It's possibly a curvy map, you know. So this might be F of CR. But the point is, F is continuously differentiable. Not just that. F is continuously differentiable. It maps 0 to 0, and the differential to the map at 0 is the identity. So what that all means is that f of x is approximately equal to x for x approximately 0. Like that's what it means altogether. See, because like generically speaking, you'd have this, right? F of x is f of 0 plus the Jacobian of f at 0 times x plus stuff. But here, f of 0 is 0. The Jacobian of f is the identity matrix. So like f of x is just equal to x for this mapping with these conditions, which is why the R cube should be pretty close. The image of the R cube should be pretty close to itself under this map. It's because it's close to the identity map, close to 0. But we can be more precise. Given this data, the image of the R cube is actually inside the 1 plus epsilon R cube. That's a kind of neat result. Let's see how it's proved. Apparently it should be easy because it's a corollary, right? Believe it when I see it. Okay, well there's the proof. So we use the previous corollary with L equal to the identity map and H equal to X in the R cube. We have f of x, the norm, max norm of f of x minus x, less than or equal to the norm of h naught times that max. But we're assuming, right, the conditions of the theorem are that this is less than epsilon. So I get epsilon times the norm of h naught, but I said h naught's equal to x, so like that is exactly that. But then we do a little bit of, well, pre-calculus, really. So check this out. So we have the absolute value. Well, excuse me, one more step. So this is a sneaky step. The triangle inequality implies that we can look at the absolute value of the norms, of the difference of the norms, right, is less than or equal to that. So this is bigger than that. Standard trick. And if the absolute value of this is less than that, then we have minus that, less than that, less than that. Here I'm just unwrapping the absolute value inequality, right? Absolute value of A less than B means that minus B is less than or equal to A is less than or equal to B. And then once I have that, I add the max norm of X across the whole thing, and it gets me to this, which then proves that f of X, the max norm of f of x is less than or equal to 1 plus epsilon times r, which says that this f of x is in the 1 plus epsilon r cube. So, whew. All right, continuing. So to say a mapping is continuously differentiable at a point means there exists some open set around the point on which the mapping is continuously differentiable, all right? Because continuous differentiability we previously defined for a set. So I'm just saying if we wanted to define it for a point, we understand that there's a neighborhood of the point on which it's true, right? So without loss of generality, an open set around the point. Okay, so corollary 1.4.28, local injectivity at a point for the map gives injectivity nearby. Suppose we have f from Rn to Rn, continuously differentiable at A. If the differential is injective at A, then there exists a neighborhood of A on which f is injective. So here's the thing. If dA is injective, then it's not equal to 0. And if it's not equal to 0, that means there has to be a minimum value m, which is attained by the norm, the max norm of this, for x in the boundary of the 1 cube. And so we pick an epsilon that's smaller than that m, and since f is continuously differentiable at a, there exists a delta, which if you're within delta units of a, you're within epsilon units of the distance of the differential from the differential at a. In other words, the differential can't get very far away from where it's at a if it's continuous near a. Like the differential itself can't rip apart from where it started because it's continuous. Anyway, so if we let U be this open set here, and we choose any pair in U, and we apply the corollary with L equal to DFA and XY equal to that, then we have, we can look at this. We have f of y minus f of x minus the differential y minus x is less than or equal to y minus x max norm times the max norm of dfz minus, I've introduced the z not to confuse the x. We had an x as the variable here before, but since x is being used otherwise, I made it z. And this was L before, but now it's DFA, because DFA is the fixed differential which we're given as injective. Anyway, so the corollary gives us that that's less than epsilon times the max norm of y minus y naught. And then we are back to the same kind of argument that we just did in the previous one. Namely that the triangle inequality then gives us that the absolute value of the difference is less than or equal to epsilon times y naught. And then we unwrap the triangle inequality. We unwrap it and it gives us this, which then if we add yield, what does it tell me? Well, it tells me, among other things, that the absolute value of, the max norm of f of y minus f of x naught is greater than the max norm of this minus the max norm of that. But by construction, we know that this is greater than or equal to m times the norm of y minus y naught. So we get m minus epsilon. So what all this means is that the norm of the max norm of f of y minus f of x naught is not equal to 0, provided we pick x and y in the open set where we were sure the differential isn't much different than the differential which is injective at a. And what that means, of course, is that f of y minus f of x is not equal to 0. I mean, the norm of f of y minus f of x, max norm of that's not equal to 0, which is to say that f of y can't be equal to f of x, which is to say it's injective, right? Because if they were equal for distinct x and y, then it wouldn't be injective, but it's not the case here. So therefore, f is injective on the neighborhood of U which contains A. So, and that's the kind of thing you need to get invertibility, right? The first step to find the inverse of a map is we need that we need to be able to solve for x uniquely, right? So let me put this away for a second here. Do a little bit more writing. So this part, I think you guys should see me write out for a minute. So this is the inverse mapping theorem. Come on, I said go up. Oh? Yeah. No! So the inverse mapping theorem is kind of what it sounds like. It's going to give us a way to find an inverse map. Well, that's not true. Well, no, it is true. It is true. It does give us a way to find an inverse map. Like the worst possible way to find it, I think, but no, a way. I say worst possible because like the theorem invites you to find the inverse mapping as a sequence, an iterated sequence of nested compositions. So I showed you guys last time how horrible that is in the one-dimensional case. I can only assume it's worse in the higher dimensional cases. So I still think in terms of pragmatic advice, if you're trying to find the inverse for a map, you probably should just try to do it algebraically, at least to start with, right? So like example